folks, I'm Keith Bowen and this is Hard Rock University. I'm on the mend, things are going well, but it's going to be a while before I get out in the field again, so for the next month or so it's only going to be classroom type videos. That's all I'll be able to do. Anyhow, today I'm going to kind of go over something I did years ago, nugget effect and sample size. Now the nugget effect is caused by the fact that gold occurs in discrete sized particles. The bigger those particles are, the harder it is to find them. If you have, say, salt and water, you've got salt molecules floating around in water molecules, and every little tiny bit is going to be just about the same ratio. So it's very easy to sample it and get a good sample for the analyzer. On the other hand, with gold, the particles are of a visible size in general. Sometimes you need a loupe, but not much more than that. And so this makes it difficult to get a number of samples with the same amount in them. The larger the sample, the easier that is to do. So how big a sample do you need? Well, here I've got an example diagrammed on the board. Let's say we started with 1 ton of rock in place. That's 27 inches on one side. And these are divided each into 10 increments. So each cube is 1/1000th of a ton, or 2 pounds. Now let's suppose this was really good ore. I mean, this is 1 ounce to the ton. That's some good stuff. Okay? And let's suppose we broke that gold up into a 1,000th of an ounce particles. Okay, we're talking something like about 0.03 grams or something like that. Okay, fairly small particles, not as small as you can see, but I mean, for placer miners, that's not anything to get excited about at all. So we got this ton with 1,000 cubes, 2 pounds each. Each cube has 1 piece of gold in it. Right here. Let me switch this way. Right here. 1 piece of gold in this corner right here at about a 1/20th of an inch across. Okay? 0.031 grams right there. Now, if you're placer mining and you're doing like a pan, well, you've probably got 2 or 3 of these cubes in it. On the other hand, if you're assaying in a laboratory, they got to break it down even further. About 30 gram samples. That's what these cubes are. All those are samples, laboratory size samples. As you can see, this has 27 cubes in it, only 1 of which has any gold. So you got 1 assay is going to run 27 ounces to the ton, and everything else is going to run 0. And as a matter of fact, 26 out of 27 times, it's going to run 0. So you would have to do a god-awful amount of assaying to get it a good number. Luckily with hard rock, it's even much smaller than this. Generally below 5 thousandths, so a 1/10 smaller than this right here. So each one of these, you know, would have several particles in it. Let's see, you know, 1 out of 27 multiplied by 1,000. Yeah, you're going to have like 10 or 20 per cube there. Now you've got some decent statistics. Okay, no matter which one of these you take, you're going to get some kind of a significant number. And it's going to vary, it'll go up and down, but at least it'll be fine. What they try and do in a laboratory setting or in a hard rock setting, you start with a big sample, like with me, like a bucket or a half a bucket at least. I'll crush it down, reduce the particle sizes to minimize the chance that that little high value hard rock gets set to the side, and the crap is what actually gets sent to the lab. So you crush it and then use a splitter. A splitter is a device that sends equal portions both ways in a statistically equivalent way. And you do that enough times, cut it in half and half and half and half until you wind up with 2 or 3 pounds in a Ziploc bag to send off to the laboratory. Okay? That works pretty well. Once they get to the lab, They will then reduce it to whatever size sample they believe is important. Then they will pulverize it. They may just likely pulverize your entire sample, but in general I think they just crush it pretty darn fine. But before the end of the process, it's getting reduced to 200 mesh minus. Simply, if there's any big particles, you want to break them up and distribute them so you can get better, more reliable, more accurate numbers. Now remember, none of those numbers was inaccurate at all. This sample was in fact running 27 ounces to the ton. These samples were in fact running 0 ounces to the ton. And none of them was anywhere close to the real number of 1 ounce to the ton. All because of sample variability. Nothing to do with bad technique or anything like that. Purely due to sample variability and the nugget effect. That's why experienced hard rock miners, whenever they see an unusually high number, they don't go with it. You start by assuming the nugget effect and confirm it before you use it. In some circumstances, you just ignore it. You just throw that one out of the calculations and use the rest, saying, it's probably nugget effect. Any error will accrue to my benefit, so why worry about it? It just depends. Now, some placer gold is pretty damn coarse. So a reasonably sized sample might be 1 cubic yard, 10 cubic yards, something like that. If you get big chunks every once in a while, it doesn't take much to make that up. So you go with these really ginormous size samples that are run through a plant and concentrated and then run through a secondary concentration. Then you pan the gold, then you weigh the gold, then you average it over the 100 tons that you processed. And that's how you deal with the problem at that end of the spectrum. So that's a quick review of how the particle size of the gold makes a big difference in the sampling and processing techniques you need to get good numbers. That's what the nugget effect is. That's why you'll hear hard rock miners talk about it a lot when it comes to assaying. And the first thing a hard rock miner thinks when he sees an anomalously high assay is that a nugget effect? So, happy prospecting and keep it safe out there.